Welcome, everyone. So today, we're going to do a really deep dive into one of the most elegant and, frankly, one of the most powerful concepts in all of finance, continuous compounding. Now, I want to be really clear right from the start. This isn't just some abstract theory or a formula you memorize for the final exam. This is a core principle that you are absolutely going to use throughout your careers, whether you end up in corporate finance, investment banking, or strategic management. Understanding this is simply non-negotiable for making sound financial decisions.
Okay, so let's start with a really big question, one that financial thinkers have been wrestling with for centuries. We all get it, right? We know that if you compound interest more often, say going from annually to quarterly, you end up with more money. Your interest starts earning its own interest faster. But what happens if we take that idea and just run with it? What if we compounded monthly or daily? Or what about every single hour, every minute, every second? Is there a limit? Is there a ceiling to this? Or does our money just spiral off into infinity? This is the fundamental question we have to answer first. This slide here really lays out that whole thought experiment perfectly. You can see the progression, right? We can just keep slicing time into smaller and smaller pieces for compounding, yearly, monthly, daily, all the way down to the second. But this brings up that really critical question. Does this just go on forever and make you an infinite amount of money? Or does the extra benefit you get from compounding more and more often start to shrink, eventually getting closer and closer to some specific predictable limit? That question right there is the heart of our discussion today.
So here's our game plan for today. We're going to build this concept from the ground up, piece by piece, so you get a really solid understanding. We'll start with the theory. What is this compounding limit? Then we'll decode the beautiful little formula that governs it. After that, we'll get our hands dirty with a real example to see how it works. Then, really important, we'll talk about the common mistakes I see students make all the time so you can avoid them. And finally, we'll see how this all applies in the real world of business strategy. All right, let's jump right into our first section. We're going to tackle that question we just posed head on. What is the absolute theoretical maximum you can get from compounding? Now, your first gut reaction might be, hey, if we compound every instant an infinite number of times, the money should grow to infinity. And that seems totally logical. But what mathematics shows us is something way more interesting, way more elegant. The growth doesn't explode. Instead, the extra gain you get from each new compounding period gets smaller and smaller and smaller until the total value converges on a very specific calculable limit. There is a ceiling, and it's a ceiling we can define perfectly with math. And that idea of a natural finite limit leads us straight to the tool we use to calculate it. This is the continuous compounding formula, and I really can't overstate how important this is. It's a true cornerstone of financial modeling. You'll see it used in everything from pricing complex derivatives to valuing entire companies. And here it is. S equals P times E raised to the power of R times T. You'll often hear people call it the PERT formula. It's a nice little mnemonic that helps you remember it. Now, I get it. The minute you see that letter E in there, it might look a little intimidating if you haven't seen it in a financial context before. But my main goal today is to completely demystify this for you. By the time we're done, every single part of this equation is going to feel like second nature. First up, P for principal. This one's the easy part. It's simply your starting money, the initial amount you invest or borrow. It's the seed capital you start with. It doesn't matter if it's $1,000 you're putting into a savings account or a $10 million corporate project. P is your starting block. It's the foundation. Next, we have R, which stands for the interest rate. You can think of R as the engine of your growth. But, and please listen very carefully because this is the single most common mistake I see, the rate must always, always, always be expressed as a decimal. So a 5% rate becomes 0.05. A 10% rate is 0.10. If you forget this step, your answer will be wildly incorrect. It's a non-negotiable part of the process. Then we have T, and T is for time. In pretty much all standard financial formulas, and definitely in this one, time is measured in years. So T is basically the accelerator pedal. It dictates how long your principal, your initial investment, gets to benefit from that growth engine, the interest rate. And now we get to the star of the show, the constant E. This is Euler's number. It's an irrational number, roughly 2.71828, and it's a fundamental constant of the universe, right up there with pi.
It is so important that you don't see this as just some random number we plug into a formula. E is much deeper than that. It literally represents the base rate of growth for any process in the universe that is growing continuously. We're talking about money in an account, sure, but also things like the growth of a bacteria population, the decay of a radioactive isotope. It is a universal law of nature that we've captured with a number.
This quote right here just nails it. I really want you to stop thinking of E as just a button on your calculator. I want you to see it as the mathematical signature of natural, continuous growth itself. You could almost think of it as the universe's own built-in interest rate. Once you internalize that, the PERT formula stops being just a formula and starts having a much deeper, more intuitive meaning. All right, enough theory. We've taken the formula apart, piece by piece. Now it's time to put it all back together and see it work with some actual numbers. Let's ground all this abstract talk in a very practical, concrete calculation. Okay, so here's our scenario, pulled right from our source material. We're going to model an investment where our principal, P, is $1,000. Our nominal annual interest rate, R, is 5%, which we of course immediately convert to its decimal form, 0.05. And the time horizon, T, for this investment is going to be 3 years. So we just substitute these values right into our formula. Our future value, S, is going to be 1,000 multiplied by E, which is raised to the power of 0.05 times 3. Now you have to remember your order of operations here. It's absolutely critical. You must calculate the exponent, that R times T part, first. So 0.05 times 3 gives us an exponent of 0.15.
And there's our result. After you calculate e to the power of 0.15 and then multiply that by your $1,000 principal, you get $1,161.60. Now, I really want you to appreciate what this number means. This is the absolute maximum, the theoretical ceiling on your return for a 5% nominal rate over 3 years. It doesn't matter if you compound daily, hourly, or every nanosecond, you cannot earn more than this.
Now, this formula is an incredibly powerful tool, but like any tool, it's only useful if you use it correctly. And as a professor, believe me, I've graded thousands of these problems, and I see the same few mistakes crop up again and again. So let's walk through them right now so you can make sure to avoid these common traps in your own work.
So here's what I want you to do. Build a mental checklist. Every single time you use this formula, just run through these 3 questions. Number 1, did I convert my interest rate to a decimal? Using 5 instead of 0.05 will give you a ridiculously huge wrong answer. Number 2, is my time variable in years? If the problem gives you 36 months, you have to convert it to 3 years first. And number 3, did I follow the order of operations? Did I calculate that R times T exponent before I touched the E button? If you can master that simple 3-point check, you will always be accurate. Okay, up until this point, I know this might have felt a little academic, right? Like we're just solving textbook problems. But now we're going to make the leap from the classroom to the boardroom. Let's put on our chief financial officer hats and see exactly why mastering this concept isn't about grades, it's about making smart, profitable decisions in the real world.
So imagine this exact scenario lands on your desk. You're a junior financial analyst. Your company has some cash to invest for a year, and you have 2 choices. Option A offers a 5.1% interest rate, but it only compounds once a year. Option B offers a slightly lower rate, 5.0%, but it's compounded continuously. On the surface, 5.1% looks better, right? It's a bigger number, but is it actually the better deal? How do you even begin to compare these two when they're structured so differently? The PERT formula is the tool that lets you compare these apples and oranges. You can use it on option B to figure out what its effective annual rate is, what it really yields in 1 year. Then you can make a true direct comparison to option A's 5.1%. And this isn't just an academic puzzle. In the real world, a calculation like this could be the difference between a good investment and a bad one, a decision that could be worth millions of dollars to your company. Mastering this is what elevates you from someone who can just plug in numbers to a real strategic financial thinker. And I'll leave you with this final thought to chew on as you continue your studies. This principle of continuous growth, it's not just about money in a bank. It is a fundamental pattern of change that you see all over the place in business and in nature. So as you go on to become business leaders, I want you to keep asking yourselves, where else could this concept apply? Could you use it to model how quickly a new product is adopted by the market, or the depletion of a natural resource, or even the growth of your company's brand recognition? The applications are way broader than you might think. Thank you.